Hello everyone, welcome to this video. In the previous videos we have seen that how can we represent the Fourier series expansion of some function which is piecewise continuous. So suppose, let me write it again over here. Suppose that the interval that is given to you as c to c plus 2l. So that means it would have period of 2l, right? And where L is some arbitrary number, C is also some arbitrary number. So that means this is an interval which is having period other than 2 pi. So for this case, suppose f of x is given to be a piecewise continuous function. So this is given to be piecewise continuous function which is single valued and fulfills all the condition, is periodic, single valued, then we already know how to write the Fourier series of this function. Then the Fourier series of this function f of x could be written like this: a naught divided by 2 plus summation n varies from 1 to infinity a n cos n pi x upon l, right, plus b summation n varying from 1 to infinity bn sine n pi x upon l. So this we already know. Where what are these a naught, a n and bn? Where this a naught, that is given by 1 by l integration from c to c plus 2l, that means whichever the interval that is given to you of the function f of x with respect to x. A n, that is given to be 1 by l integration from c to c plus 2l f of x into cos n pi x upon l dx, and similarly your bn, that is given by 1 by l integration c to c plus 2l, right, f of x sine n pi x upon l dx. So this you already know, right? So these are your coefficients which are used in the Fourier series expansion. So now we have a theorem or identity which is known as the Parseval's identity or Parseval's theorem. This theorem relate the coefficients a naught, a n and bn. So let's have a look how it happens. So for that, let me write down the theorem first. So the theorem, it says that let me write down the statement. It says let f of x be a periodic function with the arbitrary period 2l. Because we'll first study the general case and then we'll go to the particular cases. With the arbitrary period 2l defined in the interval c to c plus 2l, then we have this relation which says that you have 1 by 2l integration from c to c plus 2l of the function whole square. This thing is equal to a naught square by 4 plus 1 by 2 summation n varies from 1 to infinity a n square plus b n square, right? Where what are these? A naught, a n and b n. They are the Fourier coefficients of the function f of x. Right. So this is the theorem, the famous Parseval's theorem. So let us try to prove that. So this is a very useful result. You can see that it relates the coefficients a naught, a n, b n with that of its function's value. So let us first try and prove this theorem. So for the proof, we already know the Fourier transform of this function, so which I have defined to be here. So let me call this as equation number 1 with all its coefficient. Now what I'm going to do, I'm going to multiply both sides of this equation 1 by f of x and then integrating it from c to c plus 2l. So let me write down here. So what I'm going to do, I'm multiplying both sides of equation number 1 by f of x, which is the given function, and integrating from c to c plus 2l, the given integral. So in that case, let me show you once what is our equation 1. So this is our equation 1. So we'll multiply by f of x and then perform its integration. So on the left hand side we have integration from c to c plus 2l. F of x, one f of x was already there, so it would become now the square. This thing is equal to integration c to c plus 2l. Now you have a naught by 2. So this a naught by 2 could be taken outside and you have f of dx, because this a naught by 2 being a constant quantity is not a function of x, right? And then you have summation an f of x, summation an cos n pi x dx. So when you multiply by fx and take integral, so this would be summation n varies from 1 to infinity. You have an integration c to c plus 2l of f of x, which we have multiplied by, and cos of n pi x upon l dx. This is first quantity, and in a similar manner your last quantity would be summation n varies from 1 to infinity of bn. Now this bn is also constant, so could be taken out. So we have to perform this integration only of f of x multiplied by sine n pi x upon l dx, right? So let me simplify this. Now if you have a look at your expressions here, now from here you can clearly see that the value of your a naught, that is equal to 1 by l integration c to c plus 2l fx dx, right? So we can write the value of this thing as a naught into l. So let me see here. So you have this thing. So instead of this, what you can do, you can write a naught into l here, right? And in a similar manner, if you look at this term, so let's go back and look at our coefficients. So here, from here you can see that for the term containing cos, you can write this whole term as equal to an multiplied by l. So we have this term as summation n varies from 1 to infinity of an is as such, and instead of this we are writing an into l, plus similarly for this term we would have bn into l. So it would be summation n varies from 1 to infinity bn into l. So this is what we have on the right hand side. On the left hand side it would be c to c plus 2l integration of the function f of x whole square with respect to x, right? So this is what you got. Now look at the statement of this theorem, which says that we wanted to prove this relationship. So from here you can clearly see that we have a naught square. Yes, there is no problem. We have an square and bn square also, but together with these terms we are also obtaining l. So we have to get rid of this l, and moreover here you can see that we have l over here. So what you can do here, so you could shift this l to the left hand side so that we have the terms as required. So let me do that quickly. So here if you take l common in every term and you can shift this to left hand side, so you'll be having 1 by l integration c to c plus 2l of f of x whole square dx. This become equal to a naught square by 4 plus summation n varies from 1 to infinity, right, an square plus, now you can take the summation also common, you have bn square. Now this looks quite familiar. Here we have 2. Yes. And now let me show you the statement once more. So you see we have 2 here, 4 here and 2 here. So that means we are to divide both sides by 2. So that means this become 2, this become 4 and this also become 2. So that is what we were required to prove. So we have 1 by 2L integration c to c plus 2L of f of x whole square dx. This quantity is equal to a naught square by 4 plus 1 by 2 summation n varies from 1 to infinity of the term an square plus bn square. So this is your Parseval's identity. Now this we have proved this for an arbitrary function which is defined in the arbitrary interval of arbitrary period. So now let me discuss some particular cases. So that means whenever you see this particular cases, you could directly apply these result without going into the general expression. However, this expression should be familiar to you, right? You should use it as if it is onto your memory. So in the first case, suppose your L is equal to pi. So in that case, and your c is given to be minus pi. So in that case, your interval c to c plus 2L, it would reduce to the value of c is minus pi and c plus 2L, that would become pi. So that means we are having this as the particular case. So we are having the open interval minus pi to pi, right? So in this case, your Parseval identity would reduce to this one. So you have 1 by 2 pi. Instead of L, we are now writing pi and performing the integration in the given interval, that is from minus pi to pi, of the function f of x whole square d of x, that is equal to a naught square by 4 plus 1 by 2 summation n varies from 1 to infinity an square plus bn square, where you should note that now your coefficients a naught, that is equal to the value of 1 by L, that is 1 by pi. Integration is now performed with respect to minus pi to pi and not from c to c plus 2L, right? So that is okay. F of x dx. Similarly, you have an as equal to 1 by pi integration minus pi to pi f of x cos nx dx, and now you have a difference over here also. Otherwise, you were having the terms as cos n pi x upon L, right? So pi by pi cancels out. So we have nx here, and moreover, we have not plus, we have the value of bn as equal to 1 by pi integration from minus pi to pi f of x sine nx dx, right? So this is our first case. So in the second case, let me discuss whenever the value of L is equal to pi and c is equal to 0, then your interval c to c plus 2L, that would reduce to your interval 0 to 2 pi. So this is another interval that we see in very many examples, right? So this is our interval now. So in that case, the identity reduces to 1 by 2 pi integration from 0 to 2 pi. Now because the value of L, that is pi, right? So here we have instead of L the value pi, and the interval now reduces to 0 to 2 pi. So therefore these limits. So we have f of x whole square dx. This thing is equal to a naught square by 4 plus, now this thing is same, 1 by 4 summation n varies from 1 to infinity of an square plus bn square, right? Now we have a difference here. Now the values of the coefficients, the constants, they differ. In this case, it becomes 1 by L. Instead of L, we have pi. The only difference is in the limits. So we are having the limits from 0 to 2 pi. So this is the value of a naught. For an, the value would be 1 by pi integration from 0 to 2 pi f of x cos nx dx, and bn is equal to 1 by pi integration 0 to 2 pi f of x sine nx dx, right? So this is your formula in this case. Now we have these terms because our interval here in this case is 2 pi, having period of 2 pi. The function f of x has a period of 2 pi over here. Next we have third case. In the third case we are given that if f of x is expressed as half range cosine series in the interval 0 to L, in that case your Parseval's identity that reduces to f of x, that is given by a naught by 2 plus summation n varies from 1 to infinity a n cos n pi x upon L. So this is your Fourier series, right, with the coefficients given as a naught 2 upon L integration from 0 to L f of x dx, and your a n that is equal to 2 by L integration from 0 to L f of x into cos n pi x upon L, right, cos pi, let me write it in the next line. So we have here f of x dx, and here the value of a n is 2 upon L integration 0 to L f of x cos n pi x upon L dx, right? So this is the Fourier series, which is the half range cosine series, and in this case Bn is simply 0. You already know that. So what is the Parseval's identity here? In this case, the identity is given by 1 by L integration from 0 to L f of x whole square dx, that is simply equal to a naught square by 4 plus 1 by 2 summation n varies from 1 to infinity a n square. Why? Because in this case your Bn is equal to 0. So therefore your from this identity this term is not present. So that is the form of identity that you have in this particular case. And in the last case, whenever your function is expressed in the half range, if let me write it down, if f of x is expressed in half range sine series, so that means we are defining it, this in the interval 0 to L, then the half range sine series of this function could be written as f of x is equal to summation n varies from 1 to infinity Bn sine n pi x upon L, right? This is the series, and where your a naught and a n they are equal to 0, and your Bn that is equal to 2 by L integration 0 to L f of x sine n pi x upon L dx. So this you already know. This is the half range sine series. So in that case, the Parseval's identity that becomes simply equal to 1 by L integration 0 to L f of x whole square dx, that is equal to 1 by 2 summation n varies from 1 to infinity Bn square. So this is the identity that you have, because in this case your a naught and a n they are 0, therefore this term is not there, this term is also not there, so we have this term, right? So this is about Parseval's identity over here.